Welcome to the webinar, Principles of Extrapolation and Screening of Velocity Profiles. Just want to give a quick overview of our discussions this afternoon. Firstly, looking at velocity profile principles, velocity distribution and the theory around that, and how velocity or roughness coefficients or roughness, channel roughness itself can impact the velocity distribution. Then we will have a look at acoustic Doppler principles, which is basically the same for most of the acoustic Doppler instruments available on the market. What type of methods is available for extrapolation, and it's currently implemented in the software. Implementation in the different software packages, and some key examples, just to give you some background on the topic. Screening of velocity profiles, that is a key important thing, highlighting some of the research that's been done over the past decade. What USGS policies has been implemented to date with regard to that, and then also the implementation of the screening in the various software packages. So although most of the presentation or webinar today would be focused towards SonTek's RiverSurveyor M9 and S5 instruments, this webinar is applicable to all acoustic Doppler current profilers currently on the market, especially with the focus to velocity extrapolation and screening of velocity profiles. So if we look at the typical velocity distribution curve supplied by Vintage Chow for equal velocity, we will see that the velocity distribution is related to the geometry or shape of the channel, the roughness of the channel itself, and the presence of bends in the channel. So based on theory, if the maximum velocity would occur 0.05 to 0.25 of the depth if the channel or banks are very close, and this is specifically in channels with that is very narrow and a deep channel, such as in this triangular, trapezoidal, or narrow rectangular channels, and even on a pipe. If the channel or section is broad and there is rapid and shallow flow present, or the channel has smooth sides, the velocity or maximum velocity would occur at the surface, such as a shallow ditch and natural channel. Right, banks do not have any impact on the central velocity region if the width is greater than 5 to 10 times the depth of the flow, depending on the surface roughness. So if we have an aspect ratio of between 5 and 10, the velocity should be expected to be at the surface based on the current theory. Anything less than that, depending on the surface roughness, could result in a surface velocity or maximum velocity occurring below the surface. There's only two theoretical reasons or explanations for that to occur, is, as I said, the aspect ratio, and then secondly, if you have wind blowing upstream. So if we look at the relationship between the roughness or relative roughness and the velocity and the velocity distribution from Rouge, we will see that the smaller the roughness, the smaller the exponent for the velocity profile. And that can give you indication as well as when you do the measurements and perform extrapolation, and you are working with a small exponent, then that is directly related to the roughness in the channel itself. If the relative roughness is as a larger value, then that will also increase the exponent value. So just a quick overview of the acoustic Doppler principles that we have, and again, this is applicable to all acoustic Doppler instruments on the market. You know, the current most instruments has a different frequency range that's used, and a range between 3 megahertz to around 250 kilohertz is your traditional type of instruments used in hydrographic operations for discharge measurements. Most of these instruments are equipped with 4 beams to perform discharge measurements in both the X and Y velocity components. The system is making use of monostatic transducers, which means that the same transducer is transmitting the signal, is also receiving the signal. And when a signal is transmitted, when the transducer or that transmission is stopped, there's a ringing effect occurring on the transducer itself. And that can impact the measurements, velocity measurements. And for that reason, a blanking distance is incorporated, automated blanking distance is incorporated in the firmware to exclude that zone below the transducers or transducer face. Along the transducer itself, a number of cells are set either by using an automated process or manual configuration. So the cell size can be either automated or manual. And then using a process called time gating, we can determine the distance along the beams with the cells and then measure the velocities for each cell, as well as the total depth. So with ADCP measurements in both moving boat and stationary methods, there is a certain area that can be measured, and in this cross-sectional area is called the measured area, and then there's also the unmeasured area, which consists of the edges, a top and a bottom estimates. The edges are basically limited to the minimum depth the acoustic Doppler instrument can measure in, and the international standards requirement for edge measurements is where you are able to collect a depth where you have 2 valid cells, and then 10 samples or ensembles is measured at that specific location, and that is averaged to extrapolate towards the water edge. The top edge estimate is basically consists of the instrument drop or depth plus the blanking distance. That's the portion we can't measure, and that will be estimated. And then the bottom estimate is default in RiverSurveyor Live is 10% cutoff, and that is to prevent any side lobe interference from impacting the actual measurements itself. This is a more close-up view of those 2 top and bottom zones. As you can see there, that's your transducer depth and your blanking distance, and that is the area that we're not able to measure and will be determined by an extrapolation method. The bottom portion, as I mentioned previously, is the area where side lobe interference can occur, and for this reason, SonTek has a default value of 10% to cut off. And the main reason for this is when a signal is transmitted, there's side lobes associated with the main beam itself. And if the side lobe is reflected from a hard surface, either from the channel, bottom, or object, it can have the same strength in the reflection as the main lobe. And the software and firmware won't be able to differentiate between the two. So for that reason, we implement a cutoff of 10% to make sure that there's no side lobe data incorporated in the main data set. I just want to highlight this. This is also applicable to all side-looking instruments and up-looking instruments, where we have a cutoff. The last 10% of the data collection we don't use at all for any flow measurements or calculations. The extrapolation method is currently implemented in RiverSurveyor Live, and that is also available in all the other manufacturers' software as well as the USGS. Consists of a top, a power function, constant, and 3-point methods, and at the bottom, a power and no slip. So in RiverSurveyor Live, the default extrapolation method is a power-to-power for 1/6 power law, so it's 0.16667 exponent. And this just gives you an indication of the 3 different methods. A constant means that we are using the top cell and extrapolate that vertically to the water surface. And no slip is based on the assumption that the velocity at the boundary layer is 0. And then a 3-point method, 3-point no slip method, again, no slip is assumed that the velocity at the boundary layer is 0, and we extrapolate, we perform a linear extrapolation using the top 3 cells to the water surface itself. So the extrapolation methods implemented that's going to be discussed here consists mainly of the USGS software package, MATLAB software that's supplied, and RiverSurveyor Live. So if we look at RiverSurveyor Live, it's fairly basic. It's just an entry form using a top extrapolation. So the user have the option to select what type of method is opted for that extrapolation portion and the coefficient or exponent, and the same with the bottom extrapolation. Here you will see a 10% profile for the bottom, for discard the last 10%, and I would highly recommend that you leave the 10% value as default. If we look at Extrap, which was one of the first MATLAB software packages USGS developed for extrapolation, it displays the data collected graphically for the extrapolation process. So for you to be able to use Extrap, you will need to perform MATLAB export from RiverSurveyor Live. You can either do it manually, or we've made changes in the last version, I think from version 4.0, where you can set to perform that automatically. So as soon as you completed the transect or a loop or SMBA file, a MATLAB file will be created automatically. A normalized distance from the stream bed, a normalized unit Q is developed from the MATLAB file and displayed in the graphical representation here. Then what Extrap will do is perform an automatic fit based on the best option statistically from the data supplied. And that will be highlighted in the reference, as you can see in this image here. It will also supply a percentage difference of the other extrapolation methods compared to the discharge based on the power-to-power automated selection. If you're unsatisfied with the selection, you can change the automatic to manual and then enter a user-defined method and exponents. It is also important to note that it's using the entire measurement, which is basically the 2 transects combined. You can manually process each transect on its own. In case of Extrap, the default will be is to use the entire measurement section combined. The latest software, QREF, which is not that new, it's been out a couple of years, is also based on MATLAB, and it also requires MATLAB exports from RiverSurveyor Live to operate. It's a bit more, it supplies a bit more information on the display itself and statistical information that you can display in the graphical representation of it. This portion works exactly the same as Extrap. It will also perform an automated extrapolation based on the best fit of the data that was supplied. And in this case, it supplied a power-to-power with a 0.1485 reference. And again, calculating the difference in percentage if you use another method, extrapolation method. In this case, if we would have used the default value or default extrapolation values in the RiverSurveyor Live, it would have resulted in a minus 0.4% of the total discharge. So if we look at a couple of case studies, And that's why it's so important that at least for hydrographers that you need to analyze or at least verify your measurement sites during certain flow conditions. It's your organizational operations and requirements that will dictate if you are required to use QREF or not. I know there's a lot of organizations that does require it nowadays, but there's also organizations that prefer just to use the manufacturer supplied software. And I just want to highlight some of the case studies that we've seen before. This is one is in the Mississippi at Baton Rouge. And although we seldom get or even have flows of this magnitude in Australia, we do have, most of our catchments do generate large floods where we have from almost a trickle or very low velocities or flows to extreme velocities. So those extremes we are very used to in Australia, and that's the thing that I want to highlight in this example. So in this case at Baton Rouge, it was almost 42,000 cubic meters per second that was flowing during the flood event. And if we look at your default power to power 0.1667 exponent, you will see that there's a difference of almost 2% in discharge, which is relatively large if you take into account there's a number of other factors that will also impact the accuracy of the measurement. So if you add 2% on top of everything else that's impacting the accuracy, then obviously that will further exaggerate the variance in the measurements. If we look at the same site during normal flows, which is around 8,200 cubic meters per second, you will see that the exponent has changed from the one we've noticed during the flood event. So the important thing to notice here is that although both were off from your default settings in RiverSurveyor Live, your exponent, extrapolation exponent from low flows to high flows is definitely going to change. And that's something you need to investigate to at least verify at your measurement site to make sure you have the correct approach. The next case study is at an irrigation canal in Yuma in the USA. The total flows is around 35 or just over 34 cubic meters a second. You know, this is a type of setup that you will get anywhere in the world. It's not only applicable to certain areas. They've constructed an artificial gauging where in this vicinity here, you will see that there's a divergent canal that was constructed around this. So during the construction, they installed a cofferdam in this vicinity here to divert the water around it to do the actual construction work. During a survey, we noticed that there were some abnormalities in the velocity distribution in the channel, as well as the velocity or exponent is not your standard power to power 0.1667, where you would think fairly long straight channel irrigation uniform channel shape should be very close to that. So we performed a bathymetry survey of the channel itself, and you can see in this vicinity here on this region that the channel bed is shallower than the rest of the channel, and this is where the actual cofferdam was located. So what happened was when they finished the construction, they didn't remove the cofferdam entirely, and there was a portion left at the bottom. So during the bathymetry survey using RiverSurveyor, we also performed velocity measurements. So this is a velocity contour plot in the channel itself. So here you can see that there's the velocity distribution upstream of this, and then you get an acceleration across where the shallow portion is, or where the actual cofferdam was located. Then you get a reduction in velocity and even very slow negative velocities on the edges due to the deeper pool that's present downstream of it, and then again an acceleration right at the notch of the gauging wheel. So if we look here, you will see the default extrap method or extrapolation method selected by QREF was constant no slip with a 0.1075 exponent, and that your default value of power to power had a 0.6% difference from the reference flow. There are two factors impacting this specific site, and which is very common with a lot of irrigation sites, is there's upstream, the actual control upstream created by the cofferdam that wasn't removed. So there's an acceleration of the flow there, as well as during peak releases, this gauging web submerged in almost 100%. So your velocity distributions change depending on the flow releases in the channel. So it is important to, especially at this specific channel, to verify the extrapolation almost with every single measurement exercise to make sure that the correct extrapolation is applied. So if we look at research work done over the last decade or more on the screening of velocity profiles, the first work was identified by Gardner and Ganju in 2002 when they performed measurements with acoustic Doppler instruments to verify if it was feasible to measure much shallower conditions. So as I mentioned previously, most acoustic Doppler instruments making use of a blanking distance to remove the data set associated with that ringing effect from the transducers, as that will impact the data quality itself. And as the technology and improved and further development was done on transducers and acoustic Doppler instruments, that portion was investigated as well, where it is now feasible to measure much closer to the transducers itself, from the standard 25 centimeters when acoustic instruments was brought out to nowadays you can measure up to 3 centimeters away from the transducers. So what they've done was performing field measurements using Rio Grande Z-head in the field, and then comparing those results or measurements against Argonaut ADV at the same region from the instrument itself. So focusing on that 0 to 25 centimeters from the transducer face, that zone was targeted with ADV measurements to verify if those measurements are performed accurately enough. From their measurement results, it was identified that there was a negative bias measured in velocities near the transducer face, and that the impact on the data quality appears to be a physical presence of the transducer itself. So if you can visualize yourself, there's something in a water body and there's water flowing towards the instrument itself. Some of the water is flowing around it, some of the water is flowing right into the instrument and then falls down underneath it. And as a result of that flow distribution around and underneath the instrument, that can cause impact on the actual measurements itself. And then based on their research at that time was that the recommended depth or blanking distance specifically for the Rio Grande should be around 25 centimeters for the 1200. Further research was done by Dave Mueller et al. In 2007. Errors in acoustic Doppler profile of velocity measurements caused by flow disturbance. So what they've done here was just to relook at the data that was collected by Gardner and Ganju that was done in 2002, and then also developing a computational fluid dynamic model or CFD with the actual instruments incorporated in the model itself. They were using Argonaut or ADV instrument as well as PIV techniques to collect data in a laboratory to verify the model calibrations and to make sure that the actual measurement results is comparable with the CFD model. So in this case, you will see a velocity percentage difference in velocity if there was no instrument in the water versus with the instrument itself. So in this case, you can see around 0.2, 0.3 meters away from the instrument, you see a 1% error of the velocity itself. And then as you go further away, that percentage gets lesser and lesser. The closer you get to the instrument, the more drastic that impact is. By the time of this research, SonTek ADP was analyzed, and you will see here the graphical representation is the acoustic mode. The solid line represented on this side is the actual acoustic Doppler current profile of measurements, or the measurements performed by the SonTek ADP, and then the dotted or dashed line on the right hand side is the actual measurements that was developed from both the ADV measurements as well as the CFD model. And then the center line here is your undisturbed measurements, meaning there was nothing in the model, or there was nothing in the channel when that measurements were performed. And this will give you a percentage error bar at a certain depth away from the instrument to determine what impact that have on the actual velocity measurements. The same process was performed on the Rio Grande Z-head. Again, the ADCP portion, the undisturbed velocities measured, and then the actual measurements from CFD and ADV and PIV measurements. Then in 2010, research was done by Marian Mustang, Don Soo Kim, and Juan Castro on the same principles. A Rio Grande Z-head was used in the research, and here's maybe a more explanatory graphics to show you what was actually done. And this is a similar process that was done by Mueller et al. In 2007 as well. This is a velocity profile where there's no instrument in the water itself. Then when the instrument is installed, so this is the velocity profile and conditions that occur actually during the measurement. So these velocities are measured using a SonTek micro ADV during the tests. And then this is the results from the acoustic Doppler instrument itself. So if we look here again, similar representation of the data sets. This portion of the data shows you the actual velocity measured by the acoustic Doppler instrument. This is the portion of the data that is highlights undisturbed zone, or where there's no instrument installed. And then this is actually measured using an ADV to show you the impact of the instrument in the water itself. Dave Mueller then in 2015 did further work on a bigger range of instruments, because as you can see from 2010 there was a number of instruments, or 2007 there was a number of instruments released by different manufacturers. And from his research itself, there was a number of improvements to ADC transducers, and as I said, most transducers can now, or some of the transducer instruments can measure up to 5 centimeters from the transducer face. Field observations also show the trend for low bias near the transducers. An additional field investigation suggested that there's a disturbed flow field around the instrument itself due to the instrument. CFD model was developed during 2015 as well on a number of instruments to verify the impact of flow on the region just below the instrument itself. And from that, simulation results indicated that 2 ADCPs, the Rio Grande 1200 ZZ and RiverSurveyor M9 would allow data collection near transducer that were biased more than 1%. So from the research done by the USGS, the following basically is now applied within their software, and they've also requested that to the manufacturers themselves. So just a quick overview, and this information is available in all the research papers and USGS documentations. With the Stream Pro, using the smallest blanking distance and cell size, show no bias due to the diameter of the transducer. So again, if we come back to the why the flow disturbance occurs around the transducer is firstly associated with the size of the transducer. The larger the transducer, the bigger the impact. The smaller the transducer, the lesser or no impact there is. Rio Grande and River Pro all have default 25 centimeter blanking distances. So from the research done more than a decade ago, it was identified that at least 25 centimeters is required. Rio Pro, the minimum is 25 centimeters, which is not implemented based on the USGS website. That is accommodated for in QRF. RiverSurveyor has an auto-adaptive blanking distance process, and the center bin is always 25. The location of the first bin is always 25 centimeters from the transducer, so that puts it outside the 1% error on velocities. RiverSurveyor is 5, smallest blanking distance is 5 centimeter, and again, this is similar to the Stream Pro. The smallest blanking distance and bin size showed no bias due to the diameter of the transducer. So RiverSurveyor S5 is not impacted with any flow disturbance at all. RiverSurveyor M9, 1 megahertz is using a default of 16 centimeters, and that is programmed in the firmware. And that's also the distance that the USGS recommend the minimum blanking distance should be for the M9. And then with the 3 megahertz, the minimum is recommended as 16 centimeters. This is not implemented. The minimum blanking distance applied is done using a screening distance. The reason why SonTek hasn't implemented this into the blanking distance is mainly because some customers or users, especially in Europe, requested that they still want to see that data and they don't want it to be excluded default based on the 16 centimeter screening distance. So the screening distance in RiverSurveyor Live and QRF consists of 2 components. It's the water surface, it's the distance measured from the water surface to the bottom of the blanking distance. So in this case, it's the instrument depth of draft, and then the recommended blanking distance for RiverSurveyor Live for both the 3 megahertz and 1 megahertz by the USGS is 16 centimeters. So you will see when you're in Smart Page that there will be a value. If you add the 16 centimeters to the depth of the instrument, you will get to the same value in the RiverSurveyor Live. So from the research itself, facts using ADCP instruments with monostatic transducers that sense and receive that send and receive the signal using the same transducer. So that's a fact, and we know that. We require a blanking distance to remove the ringing effect created because of the transmission of the signal through the transducers. So from the research that was done over the past decade or so, it was indicated that the ADCP, acoustic Doppler current profiler body or housing, is creating flow disturbance on measurements that's performed very close to this transducer phase. So the actual body itself is impacting the flow patterns around the instrument and below it. And how to account for that is either increasing the minimum blanking distance in the firmware or applying a screening distance. Now, some organizations choose to follow the USGS in this regard and in other aspects, but some organizations feel they need to make that choice, decide on a data set on their own. So currently what we've done with RiverSurveyor Live has two options, which I will show later, that the actual screenshots. The one is where you can install the software without the screening distance implemented. And the second option would be to have that 16 centimeters as default implemented in the system. So that's an option you have right in the beginning when you install the software itself. When you have installed it and you perform the measurement, then you will see on your smart page on the system settings, there's a transducer depth which is user configurable. You enter there 0.10, and then a screening distance which would be calculated. So if you're using the USGS option, that screening distance will automatically be calculated, and it will always be 16 centimeters more than your transducer depth. So it's important that if you choose to use that I would recommend that you follow the USGS guidelines. Using your own screening distance raise questions because there's no research work that supports that. You could either remove a portion of the issues seen or not. So I would recommend, if you want to follow that, apply the USGS recommended screening distance of 16 centimeters. QREF on its own reprocess data using the MATLAB file, and for that matter, also the TREI data. So irrespective of what settings you make in RiverSurveyor Live or WinRiver 2, QREF will use the MATLAB file or the MMT file and reprocess all the data from start and apply the screening distance. So it is important that if you are going to use QREF in your operations, that you follow the same guidelines using RiverSurveyor Live. While you are collecting raw data, you want your settings as close as possible to QREF processes as well. Otherwise, you could go and collect data in shallow areas with RiverSurveyor Live, and then when you process it in QREF will filter the data out, and then it means it looks like it was too shallow for the instrument itself. So that is probably the most important aspect, is to make sure, if you are using QREF, make sure RiverSurveyor Live is configured or in line with what QREF is going to do as well. This is the process to install the USGS version. So when you install it, there would be an option, the second window, where you are requested, do you want to use the USGS version or not? And then you just follow the steps required until it's installed. There's an easy way to verify if it's installed. If you enter instrument depth or instrument draft in, the screening distance section will be automatically populated with 16 centimeters added to the instrument depth. With RiverSurveyor Live, from the research data that was done over the past decade or so, showed that with RiverSurveyor is a bit more complicated. It has two different frequencies, so it has two different sets of blanking distances. The 1 megahertz has a default blanking distance of 16 centimeters, so that's not affected, and the cell sizes are also larger, so there's more averaging occurring in that zone. The 3 megahertz pulse coherent cell sizes are much smaller, and the blanking distance are smaller. So in certain flow conditions, flow disturbance does impact the measurements, and the reason why the 16 centimeters was implemented, because now it applies to both frequencies, not only one. This was the reference papers that was used for these discussions, and you're welcome to. This is easily available on the internet. If you just type in the research paper names, or if you send me an email, I will welcome send you a copy of the papers if you're interested. And thank you very much for attending the webinar. I trust you had some knowledge information out of this. If there's any additional information or queries that you have about the discussion topics, please feel free to send us it through the GoToWebinar, or you can send me an email directly to my email account as well. Thank you very much. Bye.
Thanks, Daniel. Again, as Daniel said, we're now open the webinar to questions from the attendees, and feel free to either type your question into the GoToWebinar interface in the questions box, or as Daniel said, you can contact him directly at his email address, which is currently on the screen. So Daniel, I'm not sure if you can see the first question, but I'll read it for you. It says, "Hi Daniel, what is the best power coefficient to use in sites that do not have any benchmark references?"
The best power coefficients that doesn't have any benchmark references. Yeah, I think we will handle that question offline, Michael. I'm not sure those two topics are related.
All right, that's fine. So Sanish, and for anyone, if there's a question that's kind of overly technical, or we're not able to answer it on this webinar, we will be contacting you directly and sharing the answer with you. Does anyone else have any questions for Daniel? All right, Daniel, next one. Did S5 blanking distance review in Mueller have the streamlined flow attachment to the bottom of the board?
Yep, they've analyzed. That's one aspect that I didn't really focus on during this webinar. Is it's not only the actual instrument itself that can cause an impact on the flow distribution around or flow patterns around the instrument, but the platform as well. From the research that was done to date, almost all the instruments, including the Stream Pro, showed a bigger influence on the velocity patterns around the instrument if it was implemented on its own, meaning it wasn't mounted on a board, it was mounted on a post that was where the instrument was placed in the water directly without using a trimaran boat or hardboard 2 or what type of float. So that was the first obvious thing that came out of the research, is that the instrument on its own seems to generate or impact the flow disturbance around the instrument more. They did test the older boards with that ring around it, and I think that was one of the things that contributed with the larger instruments. With the S5, there's no data that from the research that suggests that the instrument or the platform resulted in flow disturbance in that first 16 centimeters.
Okay, Daniel, thank you. And on that note, here's another question. Does it work only in shallow depths? I would like to know whether the instruments work more than 3,000 meters.
All right, so these acoustic Doppler current profiler instruments, ranging from, as I said, from 3 megahertz to around 250 kilohertz, is your traditional instruments. that's used, and I would almost say 250 is a bit low. You seldom get organizations that have that, and it's more used in rivers like the Amazon and deep channels. Mostly I use between 3 megahertz and 600 kilohertz, and those instruments depth range is up to a maximum of around 100 meters, depending on the flow conditions and sediment depending on the backscatter in the water and the sediment concentration. So no, these instruments are not able to have depth ranges of that kind.
Daniel, if you use the USGS option in RiverSurveyor, does it detect if it's an S5 or an M9 and set the blanking distances accordingly?
Yes, RiverSurveyor Live automatically detects if it's an M9 or S5, and based on that will apply the screening distance. Just to confirm again that the screening distance, irrespective if you use the USGS version or the standard version, you can, if you use the standard version, you can go and type in the manual distance as well. But it does detect that for the S5s, and the same with QREF as well. That information is populated in the MATLAB files and then available to QREF. So QREF knows automatically if this is S5 or M9.
Okay, Daniel, is it preferable to have the S5 mounted flush with the bottom of the hydro board, or is there a benefit in having it project 10 centimeters below?
It depends on, and I'm going to speak here for with regard to all instruments. It depends on what the flow conditions are. If you have debris on the water surface, air bubbles, even, and I've seen in cases in the desert where there's a lot of sand on the edges and the wind is blowing, that we get dust, very fine sands lying on top of the water surface. And that starts to accumulate on top of the transducers. And that will definitely impact your measurements. So one way of finding out this, and we haven't discussed it in this webinar, is to look at your SNR profiles, signal to noise ratio, that's displayed in real time. And if you see one of the beams, one or two of the beams or even more separating from each other. So normally the SNR profiles should be closely matched. They're not going to be exactly the same. And depending on the profiling technique, if it's pulse coherent or incoherent, pulse coherent is a bit more noisy because it's smaller cell sizes. Incoherent is a bit more faulted because it's larger cell sizes. But if one or two of the beams are moving away from the group, then you know you have beam separation, and you will have to stop the measurement, clean the instrument, and continue. If that still persists, then you will have to think about lowering the instrument. RiverSurveyor Live does supply warnings in the QA box where it will tell you there's beam separation occurring. If that happens, you need to stop immediately and either clean the instrument or lower it deeper in the water.
Thank you, Daniel. You've discussed that extrapolation near the surface. How has the research been conducted near the river or stream bottom? For example, sand versus rocks versus cobbled versus weeds or plants.
There's a number of research papers in acoustic. There's definitely will be research papers in that regard. And I will have to have a look through my own documentation or contact some of the key research organizations to find it, but they will definitely be to look at extrapolation with relating to the roughness, the channel bed roughness, and type of roughness on the channel bed itself.
Okay, thank you, Daniel. Next, if we have greater water velocity, say greater than 4 meters per second, would the 16 centimeter blanking distance be sufficient, or should we set a larger blanking distance based on observations at that time?
No, the 16 centimeter blanking distance should be sufficient for that. Although saying that, from all the research papers, again, irrespective of what instrument you're using, if you're using TRDI or SonTek or Nortec, the instrument itself is has an impact on the flow patterns around the instrument and below it, as well as the platform you're using. And then something that I didn't mention is the approach velocity, and will have an impact on that as well. I think analyzing in those circumstances, what I would do is analyzing the velocity profiles in Xtrap or QREF in detail before making a decision. I can't indicate to you that the 16 would be enough or not enough. What I would recommend is perform an in-depth analysis using either Xtrap or QREF and look at the velocity profile. If you see a bend back, that could be, but then again, you need to verify if there was no wind blowing upstream as well, and the aspect ratio, if that is applicable or not. So there is certain factors that you need to evaluate before you make a decision. So it's very difficult to give you a single answer on this, because you need to evaluate all the different factors involved.
All right, and for extremely wide rivers, such as the Mahanadi in India, which has 3,000 meters, which is 3,000 to 6,000 meters wide, how is it possible to take discharge remotely without a boat?
That's with current technology, 3,000 meters. No, with current technology, if you're using, there is remote control boats that's available, that's using high range Wi-Fi. The SonTek 2.4 gig Hertz radio is able to measure a couple of kilometers, maybe up to 3 or just over 3 kilometers over open surface water, a body. But then you sit with remote control boats and their limitations. So I think you are pushing the current technology available in the market doesn't accommodate for that at this stage.
Thanks, Daniel. I don't see any other questions on the list. We'll give a few more seconds for anyone who'd like to ask a final question. Just a reminder that all these questions and their answers will be, a transcript will be created and included in the follow-up email together with a link to this webinar. That'll be available to all registrants. And of course, you can share that with any of your coworkers as well who could not attend this webinar. All right, Daniel, I'm not seeing any final questions coming in. So thank you very much for your time, sir. That was an extremely informative webinar. And we look forward to your next presentation. And to all the registrants, thank you very much. We hope you enjoyed the webinar. And there is a follow-up survey, online survey that will be coming in. Feel free to leave your opinion on this on the webinar. That feedback really helps us to improve future webinars as we go along. Daniel, thank you very much.
No, thank you very much for attending, and we'll talk soon again.
Thank you, everyone. Have a great day. Bye-bye.